So our next presentation is also a team presentation by two graduate students. Saswata Roy is a graduate student in the Furhes group, studying theoretical chemistry. And then Kapnas is a graduate student in the Craig Murray's group doing experiments on kinetics and spectroscopy.
So we all know one thing about making a movie. The director yells, "Lights, camera, action," but what you might not know is that this phrase can be applied to the subject of photochemistry. So photochemistry played a critical role in the Nobel Prize won by Sherry Rowland and Mario Molina, where they discovered that CFCs were being broken apart by radiation from the sun, and the photoproducts would then go on to participate in ozone destruction, forming then the ozone hole. What we're interested in is this very first step, when the sun's radiation interacts with the molecule. More generally, our core question is, what happens to molecules under the sun's radiation? We want to understand these gory details.
Now, even though this question might seem rather naive, we are looking at answers like how many products are formed, what are the different products formed, how much of the energy is partitioned into each of the fragments. So from a theoretical viewpoint, the actual quantum mechanical answer can be found only for 1 electrons, and the exact solution grows exponentially as we increase the number of electrons. So we have very limited hope of getting the exact answer to such a question. Now, we would be using numerical methods to understand this, and in particular, we are limited by size, so we would be looking at a model molecule, in our case, acetaldehyde. And in particular, we would be looking at one of the pathways in which the methyl and the formyl radicals are formed. And we would be looking at how much of the energy is partitioned into the jiggling or the vibrational mode of the molecule, or how much of it goes into the translational degrees of freedom. Because the internal degrees of freedom determines the further reactivity of these fragments.
So we use advanced experimental techniques coupled with high-level theoretical calculations to help us gain a deeper understanding of fundamental photochemistry. Now, I do experiments using lasers to simulate the sun, coupled with imaging techniques to help us answer some of these questions. So I use a technique known as velocity map ion imaging, where this machine was home-built in our lab in the Murray group. And so this technique allows me to be able to map the velocity distributions of photoproducts or the fragments of a molecule after it's been hit by UV light and it falls apart. And then this data can be captured using a camera. So we're going to show you then our movie called Picturing Photochemistry, starring acetaldehyde, to give you an idea of how this experiment works. So lights, camera, action. We're going to start zooming in onto the very initial point of our experiment. So what we're going to see is we're going to supersonically expand our gas molecules, which is going to cool them, meaning that the molecules are going to have zero initial internal energy. This is going to be our starting point. So our gas expands. We have a molecular beam. Then what's going to happen is we're going to take a laser beam. The laser is going to hit our molecules. It's going to fragment. Then we're going to bring in a second laser beam that's going to ionize these fragments. These ionized fragments are going to travel through a stack of electrodes that have high voltages applied to them that's going to allow us to map then the velocity distributions of these fragments. So we have our ion cloud here that's expanding, it's accelerating towards our position-sensitive detector, and bam, it hits our detector. And we take a very narrow central slice of that ion cloud, and what we see are these rings. And so these rings represent the speed at which these fragments are traveling. So the larger the rings become means that our fragments are traveling faster. And so we snap a picture of this data, and this is what we get. So we see as we scan our laser over multiple wavelengths corresponding to radiation from the sun, we see that our rings expand. And this is telling us that as we put more energy into our system, our rings are getting larger and our fragments are traveling faster. Now, all we see is what is at the very end of our detector. What we'd like to see is a molecular view of this. So I'm going to rewind our movie. I'm going to rewind it back to the point where right when the laser is going to hit the molecules. And so we want to see what exactly up close is this doing. And so this is where we're going to need theory.
So I performed the molecular dynamics simulation, but unlike the previous group that presented, we use ab initio molecular dynamics, where the electronic energies are modeled by density functional theory. And using just quantum mechanics and classical mechanics, taking no information from my collaborator, I sample a large number of these trajectories, and my data also is another movie, which looks like this. In this particular case, we can see that the methyl and the formyl radicals break apart. I do no extra manipulation. I just take statistical sampling, and I keep collecting the velocity at which this methyl fragment flies away. And this is what I see, that with increasing amount of energy pumped into the system, this is what I see, that with increasing amount of energy pumped into the system, sorry about that, we see that the methyl fragment flies faster and faster. The other degrees of freedom, the internal rotational, the vibrational degrees of freedom, do not increase in energy so much as the translation.
So we want to be able to compare then his theoretical results with my experimental results. And so just to remind you again of how we did our experiments, remember we have our cooled gas or acetaldehyde molecules that we're going to hit with laser beams. They're going to fragment. And then we're going to detect these fragments on our detector here, and we see these rings. And so what I'm going to show you then is the speed distributions that we have collected for the methyl fragment. Now I want to draw your attention to this dashed line right here. And so this dashed line represents the maximum velocity that our methyl fragments could be traveling if all energy were to be put into translation. And we see then that these distributions follow this line very nicely, telling us that most of the energy is indeed going into translation of these fragments. And so another thing I need to mention is that we are detecting methyl fragments, but due to the conservation of energy, we can also gain our insight into the other radical, the formal radical. So as we see with our results, they give us great confidence in the theoretical results, telling us then that we can use these theoretical methods to help predict other photodissociation pathways that may be difficult for me as an experimentalist to detect. More importantly, we have an arsenal of tools, both experimentally as well as theoretically, to help us further ask more interesting questions about how molecules interact with the sun's radiation, further telling us the fate of these molecules in the atmosphere.
So for further information or the director's cut of these movies, contact us at these email IDs, and thank you for your attention.
Thank you.